I've got a plan to build myself a rotary table, and that rotary table is going to have graduations around the outside of it, very much like this hand wheel. Currently I don't have a solution for inscribing those graduations, so today's video is all about designing and building a simple dividing attachment for the lathe. The first problem we need to solve is how to lock the spindle so that we can accurately scribe a line in the workpiece. And the second problem we need to solve is how to index the spindle around by a given amount. In the case of the rotary table, I want to put a division every degree, so we're going to need 360 divisions, 360 scribe lines. There are many different types of dividing attachment for the lathe, but most of the homemade ones that I've seen tend to use the change wheels, as we can see here. And what most people tend to do is to fit a spring detent that will fit into one of the teeth of the gears and to lock the spindle that way. And then the change wheels are changed to different ratios to provide different numbers of divisions. But I want my design to be more universal so I can share it with you guys basically. So I'm going to go with a more generic approach and utilise the lathe spindle, or more specifically take advantage of the hollow nature of the lathe spindle. And by doing this, I hope that the device will fit a much wider range of lathes. So this is the design that I've come up with, and it works in a very similar fashion to a spin indexer. The main components of interest are the expanding mandrel in the middle there and the two pin plates. The larger brown plate and the expanding mandrel are coupled to the lathe spindle and therefore the rotation of the spindle and the workpiece. And the smaller pin plate is held to the lathe body via the use of a standoff to stop it rotating. The core of my design revolves around this expanding mandrel, which I'm going to machine out of a solid billet of aluminium. We've got some flanges on one end to act as attachment points for the pin plates, and the other end is the part that expands. Now, there's going to be a shaft that runs through the middle with a nut on one end and a cone on the other, and as you tighten this nut, it should force the cone into that tapered section, expanding the petals and locking the mandrel in place. Next up, we've got this pin plate, and what I want to be using this thing for is to engrave machine dials. So therefore I'm going to need 360 divisions for obvious reasons. Now, to get 360 holes on that brown pin plate would make it the size of a dustbin lid, I'm sure. So the way that we're going to approach it is by using this secondary plate here, and by taking advantage of the difference in spacing between the holes in the black plate and those on the brown plate. There are 36 holes on the brown plate spaced at 10-degree intervals, and there are 10 holes on the black plate spaced at 9-degree intervals. So if you can imagine moving the pin from the 0 hole to the 1 hole, or the 1 hole to the 2 hole, then the brown plate is actually going to move by the difference between the two, i.e. 1 degree. So by using this arrangement, we can get up to 360 divisions, or any factor thereof. I've designed these pin plates to be 3D printable for ease of manufacture, and I will be sharing these on my Patreon. So if you want to build one of these yourself, then head over to my Patreon, link in the description, and you can download the CAD model for this as well as all the drawings. Now I need to make the expanding mandrel, and I'm going to use this slug of aluminium that I've got here. It's approximately 63mm by about 105, which is 2.5 inches by 4. So I've mounted the stock in the 3-jaw chuck, and I'm just facing the end off here. And what I'm going to do next is to just turn down the OD here on this one end, just to square things up before turning the workpiece round in the chuck. Now we're working with a reasonable sized chunk of metal here, at least for me. I mean, it's 2.5 inches, which is bigger than I normally turn, so I'm not expecting too much in the way of deflection when we're turning it. Having said that, we have got a reasonable amount of stick out, so I would like to bring in some tail support for extra security, so I'm going to face the end off here and centre drill it. Now that we've got that tailstock support in place, I've started turning down the OD, and the next feature that we need to machine is the flange that the secondary pin plate is going to sit on, and that's going to be 46mm in diameter, so we need to turn this whole shaft down to 46mm. Now, making prototypes of any description is a learning experience, right? And one thing that I learned on this project in particular was that mating 3D printed parts and machined parts is sometimes problematic. When I printed this pin plate component, I specified that this internal diameter should be 46mm, but of course it came out slightly undersized. So I then machined the shaft to try and fit it and ended up overshooting my dimensions. So that pin plate is actually a bit loose on that shaft, which is somewhat annoying. I think what I should have done was machined the shaft to a nominal dimension and then tweaked the 3D model to fit. And you know, it's obviously quicker, easier, and cheaper to reprint 3D prints than it is to machine expensive pieces of aluminium. Anyway, let's crack on, and we'll see if this comes back to bite us later. The next feature that we're going to machine here is the diameter that's going to slide into our spindle bore. Now, I want this to be a reasonably close sliding fit. I don't want it to be tight, but I do want it to be reasonably close so that it doesn't wiggle around too much. We keep the mandrel nice and square, and that also it doesn't have to expand too far and stress the mandrel in order to lock into place. Now, I'm going to be sharing this design with my Patreons. So if you are a Patreon supporter, you can download the 3D models for this and the drawings. I tried to make the design of this dividing attachment as generic as possible, so I'm fairly confident that it's going to fit most machines, certainly the ones with the Chinese type design. All you need is a hollow spindle bore and enough space at the back to mount and spin the index plates, as well as a place to mount a standoff that will mount to the first pin plate, and I'll talk about that in more detail later on. If you are making your own, the only feature that you should need to change is the feature that we're machining right now. That needs to match the internal diameter of your spindle bore. Mine's 38mm, but yours is probably different. So just machine this feature to be to match the internal diameter of your spindle bore. Next, I'm going to drill and ream a bore down the centre of this part to accommodate a shaft that is going to allow us to expand the mandrel. It's going to have a nut on one end and a cone on the other, and an 8mm shaft. Now, this is quite a deep hole, and I'm using a long series drill for this. This does introduce problems. It's quite a flexible drill, and we've got to be really careful not to make the drill wander off centre. So I'm taking really small pecks at this and clearing the drill regularly. Once I made it all the way through, I changed the drill for a larger diameter one, slightly undersized, and then finished it off with an 8mm reamer. The next feature we're going to make is a relief, and the purpose of this relief is to thin the material enough that it allows the petals at the end of the mandrel that we're going to make later to flex and expand into the spindle bore and lock the mandrel in place. Now, as you can see, I'm using this parting tool here to remove the material quickly for this feature, but other than the poor surface finish that we get on the bottom of the feature, this tool leaves us with one other thing that is undesirable in this case, and that's square corners. Now, as this feature of the part is going to be flexing quite a lot, square corners are a problem because they might introduce stress rises, which will then lead to cracks and premature failure of the part. So what we're going to do is bring in this round nose tool to create some fillets in those corners and to finish the bottom of this feature to 28mm. So this is where we are so far, and before we go any further, I want to remove it from the chuck and test fit it in the spindle bore. And that is just the fit I'm looking for. A nice sliding fit, no wiggle, so I think that's going to work out just perfectly. Given that I've removed this from the chuck and I'm now replacing it, we will have lost our concentricity, but I don't think that's going to be too much of an issue for this part because it's not designed to be spun at any kind of speed. It's going to be rotated by hand, so not a big deal in this case. If you were super concerned about it, you could have gone on to machine the rest of the features before doing the test fit in the spindle bore. What we're going to do now is to machine the cone in the end of the part. So I'm just moving the compound slide around there to 15 degrees so that we can cut a taper in the end of the part. And the reason that we're doing this is because shortly we're going to be slitting the end of this part to form petals, and then that'll allow a cone to be drawn into this taper and to expand those petals and lock the whole mandrel into the spindle bore. And we're just going to finish this part off with some nice chamfers. And yeah, another classic Jonesey bonehead move there. I ran the tool into the work as I was retracting it. So yeah, we're going to need to sort that out. And I'm going to machine in a nice taper here to delete my mistake. Actually, I don't think that looks too bad, so let's pretend that was supposed to be there from the start, shall we? And we're going to flip the part round now so that we can machine that largest flange to final size. Now, I could have brought this to size in the first operation when we were squaring the stock up, but I suspected that this being aluminium, these hardened steel jaws might chowder the surface up, so I wanted to leave myself a little bit of stock just to clean it up and bring it to final size. As I mentioned earlier, fitting 3D printed parts to machined parts can be a little bit problematic in that the 3D prints often don't print to exactly the size that you expect them to. So, for instance, this larger pin plate I printed to exactly a 62mm internal diameter, and it came out a bit smaller than that. It came out about 61.6 or something. And also, depending on where you measure the 3D print, you can get different readings because of the ridges in the plastic and because there's slight deformations with the plastic cooling and so on and so forth. So I'm trying a different technique here. I've machined the main flange to 62mm, and obviously that doesn't fit. So I'm going to take another cut, just a skim cut, and try it again, and then rinse and repeat until it does just fit. So this is exactly the fit I was looking for. It's quite a tight push fit, but yeah, just what I needed for this part. And in hindsight, this is the technique I should have used for the last part. I just need to finish up that flange by facing it to the correct width. And then, as you can see from this 3D printed part, we've got holes in it for bolts. So we need to go over to the mill now and drill that bolt hole pattern. We need to locate the part in the mill here so that I can line the DRO up and drill this bolt hole pattern. So doing that with a pin, as you can see. And we don't want any more bonehead moves, do we? So I'm going to do an idiot check here and put the part on and use a little Sharpie there just to fill in the holes, just to make sure that we're roughly in the right place for this bolt hole pattern and we're not doing anything terribly wrong. Hang on a minute, that tap is slipping in the chuck. That is not a good sign. We're going to have to finish this by hand. I'm tapping this M3, which is a lot thinner than it looks on the camera here. And this is quite a deep aspect ratio hole. And given that it's aluminium, which is quite a gummy metal, you need to be pretty careful, otherwise you can end up breaking taps in this kind of situation. Which, given the amount of work that we put into this part already, would be super annoying. Wait for it. Oh man, you had to see that coming, right? Oh dear me. Bonehead move number 2 of the day, and that was the last hole as well. Never mind. Let's see what we can do about fixing it. So here's our broken tap from the other side, and that is going to interfere with the 3D printed part, so we can't leave it like that. I'm not going to be able to get this out, so my only option really is to grind it flat. And we're going to have to make do with 5 bolts instead of 6, and I don't think it's going to cause a problem in this situation. It's going to be plenty strong enough. Incidentally, if you guys have got any tips and tricks for removing broken taps from workpieces, I'd be more than happy to hear from you in the comments. This isn't the first tap I've broken, and I'm pretty sure it's not going to be the last. And now to create the slits that are going to form the petals to finish off this expanding mandrel. I could just do this with a hacksaw, but I'd like it to be a bit neater and a bit more uniform. So what I want to do is to create 6 evenly spaced slits around the circumference of the part using a slitting saw. I've got the part bolted to this thin mandrel here, and I'm going to use this to mount it in the 5C collet in the spin indexer. We're going to use the spin indexer to rotate the part by 60 degrees in between each cut. Now this is going to be an extremely sketchy setup. We've got a very long part mounted on a thin shaft, a load of stick out, and no tail support. And the reason we're doing it this way is because it's an awkwardly shaped part. It's got that big flange on the one end, which makes holding it in the vise between V blocks very awkward. And we also need clearance for the slitting saw on this end. So yeah, I figured that I'd take my chances, and it would probably be okay if I took light enough cuts. But actually, as I'm discovering here, it's really not rigid enough to cut all the way through. So plan B is to continue with the slitting and to use these machined slits as guides. I'm going to finish it off manually in the vise with a hacksaw. And that didn't go to plan either. So as you can see, the saw blade has wandered off. It's started in the slits at the top there, but as we've got further down the cut, it's migrated and looks like a right pig's ear. So that would have gone a lot better if I had a bandsaw, but I don't have a bandsaw. So there we are. But anyway, this is a functional part. It doesn't need to look good. It's going to be inside my spindle bore, not on my mantelpiece. So as long as it works fine, then I'm happy with the result, I think. Now, before we can start testing, we've got 2 or 3 other parts to make, and the first is this standoff. It's a quite simple turning job. I'm making it out of brass. It's got a M6 threaded rod on one end and an M6 threaded hole on the other. And the purpose this serves is to lock the first pin plate against rotation of the second pin plate. This will make more sense when I do a demonstration shortly. One of the most crucial components of the whole assembly is the cone that we're going to make right now out of mild steel. This cone sits on the end of a shaft, an 8mm shaft that goes through the entire mandrel, and on the other end of the shaft is a bolt that, once tightened, will draw this cone into the mandrel and expand those petals that we cut earlier on. So I've just cut the thread for the shaft, and now I've set the compound slide over to 15 degrees to match the taper that we turned on the cone inside the mandrel earlier on. Just cleaning up that dodgy looking surface finish there with some emery cloth, and the next job is to bring the part to length. Then we're going to part it off, and then we're going to flip it around in the chuck and screw it onto a screw mandrel to finish the other side. These are the two 3D printed components, and this red one here is the front pin plate. It's got a number of numbers and holes in the front, which I'll explain in more detail in a minute, and a fixing there for the standoff that we made earlier. This is the rear pin plate. We've got 36 holes in this, numbered around the outside every 10 degrees, and the bolt hole pattern there is for fixing the expanding mandrel. One thing to note with these 3D printed parts is that they do print a little undersized sometimes, as I mentioned earlier. So coming back in here with a 4mm reamer just to open those holes up so that it fits the pin that I made off camera, which you can see here. This is just a stainless steel pin with a tapered section on the end and a brass head on the other end. So we're on to final assembly now, and before we get to the testing, I just want to explain briefly how I intend this mandrel to work. So this shaft has a nut on one end, and as you tighten that nut, it draws the cone into the tapered section of the mandrel, expanding the petals and locking via friction the mandrel to the inside of the spindle. Or that's the plan, at least. So let's start by installing our standoff. It's going to replace an existing standoff that's there to support the cover. The one that I've made is slightly longer and has a different fixing on one end. And now we're going to screw the front pin plate to this standoff, and we're going to use this as an anchor point. It's fixed here, and it's also fixed to the mandrel itself, so that when we push a pin through this plate into the back plate, we can actually lock the rotation of the spindle. It also allows us to index the spindle by moving the pin to different holes. All we need to do now is to nip up that nut to expand the petals inside, and the rotation of that black plate should be coupled with the spindle. And that I'm really pleased with. Honestly, I couldn't be happier. With the slightest pressure on that nut, the mandrel has locked solidly in the spindle shaft, which is just what we want. We have this white mark here, and that's what we use to read off the angular position on the black dial there. So if I get the pin and pop that into the 0 position on both the front plate and the back plate, we're now at the 0 position for the spindle. And there's no perceptible play in the system here, which is great news, because if there were, then that would affect the positioning of the workpiece in the spindle, and therefore the accuracy of any features that we're intending to machine onto that workpiece. Now we'll use this pin here to select some different angular degrees. Now this front pin plate has 10 holes numbered from 0 to 9, spaced at 9-degree increments. The black plate, the one at the back there, the holes on that are spaced at 10 degrees, so the difference between the two is 1 degree. So therefore, every time I increment the pin by 1 hole, we move by 1 degree. And we continue like this all the way around to 9, and then to get to 10 degrees, we move the pin back to 0, but lined up with the 1 there. Now, because of the parallax error in the camera, it looks like we've gone past the mark there, but it is actually lined up with the 1 exactly. And now on to some testing, and what I've done here is I've blued some stock up in the chuck, and I'm just scoring it with my centre height gauge here and indexing around 10 degrees for every pass. And initial results are promising. It looks to be working exactly as I intended it to. So time now to move on to some finer resolution gradients. So I'm just putting in every 5 degrees now, and that too is also looking fine. So I'm going to move on to 1 degree increments. On first inspection, I thought we were going to be just fine with these 1 degree divisions, but on closer inspection, you can see that actually some of the spacing in between the divisions is somewhat unequal. I think at least some of the problem is the fact that I'm using this centre height gauge as a scribe, and I'm moving it around on my cross slide here over these oilers and so on, and it's not a very stable platform. So I'm going to try again with one of my HSS threading tools turned on its side in the mounted on the tool post. Hopefully this is going to be a bit more stable. So that has made a bit of an improvement. It's still not perfect. As you can see, we've still got a small error, I think. Probably not more than 1/4 to 1/2 degree, but there is this little bit of variation between those single degree graduations in some cases. So there's still a bit more debugging to do. I think I'll do that in the next video. I think the next thing to look at probably is the fit between that red pin plate and the mandrel. I think that's probably the culprit here. But overall, I'm really pleased with the progress so far. One other thing I think I could improve is the consistency of these graduation lines, which will be the subject of the next video when I build this rack and pinion graduating tool. This tool should be superior in many ways to the one I've just been using, so if you're interested in seeing that build, then please consider subscribing and hitting that bell icon so that you're notified when the next video comes out. As I said earlier, if you're interested in making one of these for yourself, then the 3D files and the plans will be on my Patreon, link in the description below. Thanks very much for watching until the end, folks. I really appreciate the support and hope to see you next time.